Okay, I guess we go to the next one. That is Liwen Xu, Demystifying Resolver Works.
Okay, so yeah, good morning, everyone. I'm Liwen from ETH Zurich. And looking at the topic, I'm not here to propose yet another attack, which does not only exhaust the resolvers, but also the designers. So actually, today I'm going to offer a formal perspective on the DNS-OARC to make it more precise and tractable so we can analyze and understand it more systematically. So looking at the traditional volumetric tag, you need a botnet, you need many queries and large traffic volumes, and DNS servers here are just collateral damage. And work amplification is something fundamentally different. The attacker only needs a few queries and cause the resolvers to do a disproportionate work. And we coined this term with our previous talk at DNS-OARC 43 to distinguish it with the conventional reflection amplification attack. So this is actually not a new observation. RFC 1034, written in 1987, has already identified the risk. But what it left undefined is a precise definition of work and ways to measure it, also the guidance on the bound. So given that, what is the maximum amount of work a resolver can perform for a single query? And for 40 years without a precise answer have some actual consequences. Because we're caught in a break and fix cycle, so over the decades, a steady stream of attacks have been proposed, and each of them exploit a new attack vector and then result in new patches. But the questions we cannot answer with this paradigm is that, are there more attacks like this, and how many more? And without a formal foundation, we cannot know. So, right, all these kinds of attacks are driven by informal intuition. Smart people figure out that something looks suspicious and then trying to figure out a way to exploit it. But the insight we bring here is, let's go back to where it all started. So the top-level algorithm in RFC 1034 has already gave the ground truth. And it's actually a 4 steps loops. It loops itself until the final answer is reached. So here is actually a restatement of the algorithm we just saw in the previous slides. And from this formalization, we model the recursive resolution as a transition system. And here, all the 4 cases in the algorithm can be seen as a specific state transits in the transition system. And S here denotes the set of states, which are the distinct stages of the recursive resolution. And sigma here is external input, like the response from the authority name servers. And the delta here is a transition function that maps the current state and the external input to the next state. So here we highlighted the 4 subsystems we just described in the previous slide. And then we further extend the model with state transitions where the named server addresses are missing, the TC bit is set, and the DNSSEC validation is requested. So this forms the 4 components of the critical path of this recursive resolution process. So modeling the state transitions actually makes the resolver behavior tractable. While the transitions capture the structural features of the recursive resolution, to reason about the resolver work, we need to annotate costs to these transitions. So we introduce the cost function C. It captures 3 types of cost. First is outgoing query processing cost, which is related to the R size, R count, and also the cacheability. And the second one is the DNSSEC validation cost. It depends on the algorithm you use, the key size, also the number of R's that you need to validate it. And the final one is a fixed transition cost, which serve as a baseline of the state transition. So yeah, annotating transitions with cost makes the resolver work quantifiable. And now it's obvious that the transition system has loops, right? It can cycle indefinitely, but in reality, the resolution needs to terminate. So to reason about that, we also introduce V, the counters, to track the cumulative number of loops it has already traversed, and also L, the constraint, to check at each step whether the current path is still available or legal. So putting this all together, we reached our final model. We call it the extended transition system, also the ETS, and also the further analysis was all based on this formal modeling. So now with the ETS at hand, we can actually formulate our problem more precisely. The total work of a resolution is actually the sum of the cost along its state transition path, because a resolution is basically a path from S0 here is the start and SF here is the end. And now we can also answer the question we brought up previously, that the upper bound is actually to maximizing the cumulative cost through S0 to SF. So it's a basic mathematical problem. And then we show how we can actually solve it. So the ETS can be seen as a graph, and the states are nodes, and the transitions are directed edges. Also, we annotated cost and model it as a distance between the different nodes. So the maximum work problem is actually equivalent to the length of the longest path in the graph from S0 to SF. And then to solve that, we designed a constrained longest path search algorithm based on the A-star search algorithm, which is a shortest path algorithm, but we trigger it a little bit, and then we give the negative value of each edge weight so we can actually find the longest path with the shortest path algorithm, of course, a variant. And it features a priority search and constraint checking, also gives termination guarantees, and output traces and maximum work are provable optimal given the conditions of state completeness, additivity, and boundedness. Well, here is an example of the traces produced by longest path search algorithm, but it's just an abstract of recursive resolution. But actually, to drive the resolver through it, we need to make it more concrete. We need real DNS responses. But the standard name servers cannot do that because it's stateless, it's based on static zone files, and cannot track the procession states or histories. So we propose a component called DRN, also the dynamic reconfigurable name server, which can generate responses dynamically and full session aware across queries and give full control of the content, timing, and ordering of the responses. More importantly, it can also mimic distinct name server identities within dozens of these kind of name servers within a single instance. So the DRN combined with the algorithm, also the model, forms rProfiler, our end-to-end DNS-OARC profiling system. So here are some examples of what the profiling actually finds. I'm not going into the details of it. And actually, we found that some constraints are implicit. The constraint here refers to the constraint that we used in the transition system because we need that to bound the loop in the search algorithm. So we found that some constraints are actually implicit, only discoverable through the proving. For example, if the DNS the TCP retry queries account towards the global quota of the algorithm queries, and also that if the DNSSEC related queries account towards that DNS quota, algorithm query quota. Sorry. So with all the parameters in place, we can now compute the traces for the three types of resolvers we have just tested. And here is the results. So with one single query, the 2x9 can trigger more than 1,000 algorithm queries, and dozens of megabytes of data transferred, and the data for unbounded power DNS are lower, but still kind of severe. So we just saw what a single query can do. Now, what if we kind of sustain that query, that stress over time? So we start the stress at 30 QPS and also maintain a benign query sending rate at 30K QPS. And results are shown here. I'm not going to dig into the details of it. You can find it in our paper. So well, in all three cases, the performance degradation is actually like very severe, like at least 67%, and in some cases, the resolver is completely taken down. So let me add something. So the green lines here are the QPS of the legitimate clients, and the orange lines here are the latency of the legitimate queries. So, right, let me summarize. As early as RFC 1034, the authors remind us to bound the amount of work a resolver can do. And now we have a methodology and tools to formally define and compute that bound. And also, through the profiling, we find that resolvers remains vulnerable even with all the mitigations in place. And actually, the performance degradation is multifaceted. That's the part that I kind of omitted. But sometimes it's related to the cache evictions. Sometimes it's related to the TCP stack, et cetera, which is exactly the reason why a per attack and ad hoc solution is insufficient. And also, it was a point towards a bigger goal here, like the end-to-end availability guarantees for the DNS. So achieve that, we first need to understand the resolver work, which is the work we did here, and also the DNS, the RFC disambiguation, which can eliminate the disambiguities in driving the resolver implementations. And finally, we probably need to proactively schedule the resource of the resolver so it can prevent it from being overwhelmed. Right, so our full papers are here. If you're interested, please scan the QR code, and I'm happy to take any questions. Thank you very much.
Paul Hoffman, ICANN.
Yeah.
Deleg. You didn't have deleg in your chart. It will make it harder. I think it'll probably be parallel to NS, but okay. Before you finish, please throw that in.
Okay.
Thank you.
Thank you. Thank you.
Giovanni Modas, IDN Labs and TU Delft.
Mm-hmm.
Thanks for the work. I mean, this is fascinating work. I have to read this paper.
Thank you.
Did you actually notify the developers of resolver software when you found those things? Did you notify them?
Yes. So these are exactly the real traces that we have in the
Did you tell them about this?
Yeah, we did the responsible disclosure. And so actually we kind of have a very long communication process with Spine9. So previously we thought this was because of the cache eviction algorithm, because you can see here, it's the performance degradation is always related to the cache eviction. I didn't put the figures for the RAMs and CPUs here, but yeah, actually they are. But later we realized it's probably related also to the TCP stack.
Yeah.
So yeah.
Did they fix any of it?
Yeah, I think there is a new release for the TCP problem, but I don't know the cache mechanism.
I think there's some from Bine here.
Oh, sorry. Yeah. Hi. Oh.
Petr Špaček, IC. I was one of the persons handling this. First, thank you for responsible disclosure. It was a pleasure to work with you because unlike many other people, you actually explained what you are doing and why and what's the impact.
Yeah, thank you.
Having said that, this type of attack is very complicated to handle because very often there is like multiple contributing factors. It's not like one bug you fix. But in this case, besides other things, it was exploiting existing known performance limitation in Linux kernel plus other things together. So that was really a pain to work around. And thank you for being patient because it took literally months in the responsible disclosure process until we figured out what to do with it. So thank you very much, and we need to talk after that.
Yeah, exactly. Yeah. I also want to add that, I mean, the main idea here is not to propose yet another attack because people got exhausted. So we want to provide a methodology or like a way or tools to help people to figure this out, or to at least to measure what the impact is. Yeah. Thank you.
So I'm relaying a question from
Yep,
Joe Abley, who says, 1, great work. 2,
thank you.
The use of secure transports between stub and recursive and between recursive and authoritative in the future involve new costs that scare a lot of people. Have you considered modeling different strategies in session and query management in those scenarios using this framework?
Yeah, that's a great question. Actually, I want to add something here, but I don't know if I have enough time, because the model here, actually, you can treat them like you can annotate the cost as I described, and also you can also annotate the cost based on the system, like the CPU cycles you need, or the size of RAMs you need. Also, like if you want to extend to the relation, like to the authority name servers or the whatever, yeah, I think it's extensible. Yeah, thank you.
Thanks a lot, Liwen.
Thank you.